Hello, everyone, and welcome to this talk from our Resilience of Autonomous Systems seminar series. It's a great pleasure for me to introduce today's speaker, who is a close collaborator, Javier Camara. Javier is Associate Professor at the University of Malaga and also a researcher at the university's Institute for Software Technology and Software Engineering. Prior to that, he's been a lecturer in the Department of Computer Science here at the University of York, and he maintains an honorary visiting fellow position with our department. He was also a senior systems scientist at Carnegie Mellon University's Institute for Software Research, and has held a number of similar postdoctoral research positions at other leading research centers in the past. He has also been program chair of the Symposium on Software Engineering for Adaptive and Self-Adaptive Self-Managing Systems in 2022, and a PC co-chair of the International Conference on Formal Aspects of Component Software this year. Now, in this talk, he's going to cover concerns associated with the engineering of self-adaptive systems. And as you can see, he will in particular tell us about the uncertainty interaction problem in adaptive systems. I spoke to Javier, and he's happy to receive questions during the talk if you have them. So please let me know in the chat if that is the case. Javier.
Well, thank you very much, Radu, for the kind invitation and presentation. So today I'm going to be talking about this uncertainty interaction problem in adaptive systems. But before doing that, I would like to acknowledge the fact that these ideas have been developed in collaboration with these colleagues that you can see here in the slides. So first of all, I'd like to start by introducing some context about this uncertainty interaction problem. So we all know that software-intensive systems are increasingly used to support many tasks across domains, and that they have to operate under high levels of uncertainty. So these uncertainties may arise from interactions between software and physical elements in cyber-physical systems, for instance, humans in the loop, machine learning-enabled components, or even the lack of control over third-party components and services. So, of course, we also know that assurance is critical. So I should be able to provide evidence that these systems are going to behave as expected when they're operating. So it is difficult to provide such evidence sometimes with uncertainty sources alone, but it becomes even more difficult because sources of uncertainty tend to be dependent very often. So uncertainty interactions can affect the achievement of system goals in subtle and often unpredictable ways. So to make this more concrete, I would like to give you an example of a system in which we have a mobile robot that is tasked with moving to a specific location in a physical environment that is marked in the illustrations that you can see in the slide. And this robot has to move around with limited battery and is affected by two different sources of uncertainty. So one would be imperfect sensing. So in this concrete example, we're going to assume that the robot can operate with two alternative sensors. The first one being a camera, which we're going to assume has no uncertainty. So it is very reliable at detecting obstacles. The other one is a LiDAR, which has limited ability to detect obstacles. So depending on the geometry of the obstacle, it may be the case that sometimes it is not going to be detected. The other source of uncertainty would be the environmental uncertainty. So in this case, knowledge a priori about the corridor on the left being dark. So in some variants of this scenario, the robot is going to know beforehand that that corridor is dark. In some other cases, that knowledge won't be available a priori. So let's look into 4 different variants of this scenario. So the first one is a variant where we have no uncertainty. So the robot knows a priori that the left corridor is dark, and it is operating with a camera. So in this case, the robot is not going to have any problems arriving to its destination because it's going to go through the right corridor without collisions, and that's going to be it. In the second variant, we're going to assume that we have environment uncertainty. So in this case, the robot doesn't know that the corridor on the left is dark, but it's still operating with the camera. So when the robot tries to reach the destination, it's going to go first. It's going to try first the left corridor. It's going to eventually find that it's dark, and it's going to replan and go through the right corridor. And before finishing the mission, it's going to stop by the charging station that you can see in the corner to replenish its battery. The third variant is one where we have sensing uncertainty. So in this case, the robot knows that the corridor is dark, but it is operating with the LiDAR this time. So in this case, the robot is going to try the right corridor, and it's going to eventually collide against some obstacle. It's going to need to replan at some point, and inside that plan, it's going to incorporate an action for recharging the battery. So the battery is going to be replenished before arriving to its destination. And finally, we have a fourth variant in which we have a combination of sensing and environment uncertainty. So in this case, the robot doesn't know a priori that the corridor is dark, and it is operating with the LiDAR. So this time, the robot is going to try the left corridor, eventually collide against some obstacle, try to replan, and it's going to try to reach the destination through the right corridor, but before arriving at the charging station, it's going to run out of battery. So in this case, what happens is the two sources of uncertainty combined are going to prevent the robot from satisfying the goal of its mission. So this is just an illustrative example, but well, the idea is illustrating some broader vision that we have, in which we consider that the management of uncertainty interactions must be a first-class systems development problem. And in particular, we believe that modeling plays a central role in managing such interactions. So we envisage reusable patterns that are going to be able to, or they're going to enable us to explicitly capture uncertainty interactions, use models at runtime to detect potential interactions, facilitate interoperability between modeling paradigms, etc. So the idea is that ultimately this will enable us to arrive to a situation in which we're going to have more efficient development paradigms of high-quality software-intensive systems. So before we get there, of course, we have a very long road ahead in which we have to answer some key questions. Well, some of them might be what kind of modeling patterns can be developed to represent different types of uncertainty interaction? How can modeling notations enable better compositional analysis of system properties? What types of automated analysis can be applied to models to detect uncertainty interactions? Or how can models at runtime be used to manage uncertainty interactions as the operational context of the system changes? So answering these questions is going to entail addressing some challenges in the representation, analysis, mitigation, and also exploration of uncertainty interaction. And we're going to discuss these during the rest of the talk through the lens of modeling. So, but before we continue and we start listing those challenges, I'd like to give you another example about uncertainty interaction in the context of znn.com. So znn.com is an exemplar that is broadly used in the area of self-adaptive systems, and it consists of an adaptive news website infrastructure that is built with a MAPE-K paradigm. So in ZNN, we have a pool of replicated servers that are connected to a load balancer, and I can dynamically, well, the system can dynamically activate and deactivate these servers to cope with different levels of workload. So it also has a set of quality objectives like cost, quality of the contents being served, performance. But in this case, we're going to focus just on performance, just for simplicity. And performance in this case means keeping the request response time for legitimate clients of the system below some threshold so that the system can be responsive as it is providing service. So what are the sources of uncertainty here in znn.com? Well, we have several categories. The first one are models. So models of course, can be specified at some level of abstraction, and they're not going to describe the system in full detail. They can be incomplete. One example of this might be the discretization of the response time property. So the values that we observe in the system ultimately are going to be incorporated into a model that is going to be used for analysis and decision making, and this is done with some level of granularity. We also have adaptation functions. So we have imperfect sensing, actuation, latencies in the actions that the system carries out. One example of this is the time required to activate a server, which can range from several seconds to several minutes. So of course, we have some uncertainty in there too. We have goals, which are captured in this case by means of utility functions. So we have cost minimization, performance optimization, etc. And we also have environment. So of course, the environment is predictable only to some extent. So there are fluctuations in resource availability and evolution of different parameters that we can predict only in a very limited manner. So one example of this would be the evolution of the request arrival rate in ZNN, and also the fact that servers are able to spread the workload only with some level of reliability. It may be the case that I try to activate a server and that is going to fail. The server is not going to boot properly, for instance. So in this context of ZNN, I would like to give you an example of uncertainty interaction in a specific situation, which is the one where we're trying to activate a new server when the response time property goes above a given threshold. So in this case, we're designating our response time property by R, that is our ground truth value for the response time property, and the threshold is going to be R max. So the two sources of uncertainty that we're considering in this interaction are going to be adaptation functions, and concretely the imperfect sensing of the response time property. So the offset value of that response time property is something that we're going to call R hat. And we also have model abstraction, which is the discretization of the response time property. And in this case, whenever we have the discretized version of a value, we're going to call it with the subindex D. So in this case, we have RD for the discretized version of the response time property. So if we look at the illustration that we have in the bottom of the slide, we can see some rectangles. And overall, it represents a section of the possible range of values for the response time property. That's what we have on the horizontal axis. So we have different discretization buckets represented by those different rectangles, and we have the depiction of the Rmax threshold. So we have a discretization parameter mu that controls the granularity of that discretization process. And whenever we measure a value within one of those buckets, we're going to assume that we're snapping that value to the center of the bucket, and that's the value that's going to be stored in the model. So let's imagine that we are measuring this response time value here in this example. So we're measuring this value on the right bucket, and that is the ground truth value. But actually, what we are sensing, what the system is reading, is this sensed value, this R hat, that is, of course, with some sensing error, so which we're going to call kappa in this case. So once we have that sensed value, what the system is going to do is discretize that value. So we're going to snap that R hat value to the center of that bucket, and that's the value that's going to go into the model for analysis and decision-making purposes. However, if we didn't have that kappa, if we didn't have that sensing error, the discretized version of the response time would be where RD is in this illustration that you can see on the right bucket. So what situation do we have here? Well, we have a situation where the value that goes to the model stays below the threshold R max, whereas the values for both the observed response time and the discretized version of the response time without the sensing error are above the threshold. So what this is telling us in this case is that independently, the discretization and sensing error do not prevent the triggering of adaptation, but together they do. So in this case, we have a situation where we would need to activate a server to reduce the response time of the system, but we're not doing that because of this uncertainty interaction. So we wanted to investigate a little bit more examples such as this one, and we conducted small experiments where we, for instance, modeled CNN.com using a probabilistic model checker, PRISM, to analyze what would be the impact of such interactions on the goals of the system. For instance, in this case, it would be accrued utility. So we're considering only performance in this case, we modeled the system as a set of interacting processes that capture the behavior of different parts of the system. So we had a model where we had a module or process for the system that describes how requests are served. We have another process for the sensor that captures the response time property with a given level with an associated error that we are able to control through a parameter. We also have a module for the discretization that, again, we're able to control through a parameter that encodes different levels of granularity. And finally, we have an adaptation module that captures the behavior of the self-adaptive layer and the actions that are carried out of the managed subsystem. So, for instance, the activation of servers and so on. So we wanted to assess what would be the discrepancy between the utility that we would actually get in the system when we have and when we don't have uncertainties in place, right? Associated with the discretization of the values in the model, and also with the observation of the values through the sensors. So what we did was encoding a reward structure, a quantitative reward structure in the model that was associated with the delta between the ground truth values of the response time and the versions of the response time that would go into the model. That is the discretized version of the observed values. So the results showed some significant increment in discrepancy between ground truth and measured utility when uncertainty sources interact. So here on the right-hand side, you can see an illustrative plot where we have a red line in the bottom that shows no discrepancy at all because there's no uncertainty in this case. We have other dashed lines that correspond to individual sources of uncertainty where we can already see some discrepancy. And we also have the solid black line at the top with uncertainty interaction, where we can see that there's even a more remarkable discrepancy when we combine these different sources of uncertainty. So this is just an illustrative example, and well, there are more of these in one of the papers for which I'm going to provide a reference at the end of the talk. But I'm also sure that this may bring some examples that you may have seen to mind in some other software systems. So the idea is that we wanted, motivated by this, we started compiling a list of challenges that we would need to address if we want to improve the situation and start being in a position where we can mitigate this sort of adverse effects in a systematic manner. So we divided this list into several categories, the first one being modeling. So I'm going to briefly go through those. The first challenges that we have in modeling are related to improving current modeling notations to represent and manage uncertainty. So although the representation of uncertainty in software models is improving, we're still far from having sufficiently good solutions. So for example, representing uncertainties that we have identified earlier in our example in CNN.com is not possible with most of the modeling notation that we have currently available. So we need more expressive modeling notations to represent and manage uncertainty at different levels of abstraction. The second one would be high-level modeling. So beyond representing the individual uncertainties, we also need to be able to indicate at a very high level of abstraction what uncertainty interactions are likely to take place. However, models at a very high level of abstraction are typically unable to capture and manage the individual uncertainties with the required degree of precision. So hierarchies of related model capturing uncertainties at different levels of abstraction could be an option to address this challenge, would be something to explore here. We also have a challenge related to uncertainty interaction modeling. So it is important to be able to represent how uncertainty sources are likely to interact, and not only if they're able to interact, as in the previous challenge, in challenge M2. So identifying the most suitable representation and underlying logics to capture the interactions and their possible emergent effects. As it's difficult because given that we have different levels, different types of uncertainty, we are not going to have a uniform notation that is going to be capable of representing all types of uncertainties. So that is going to be very challenging. In addition, models at different levels of abstraction can generally be very difficult to combine, so that adds to the challenge as well. So the second category is analysis, and here we have several challenges. The first one related to the integration of uncertainty analysis. So analyzing different classes of uncertainty may provide results that are qualitatively different, and this makes their integration challenging. So for instance, if we are applying statistical analysis to analyze measurement uncertainty, this is going to produce confidence intervals, whereas probabilistic modeling techniques that we use to analyze dependability or performance properties are going to typically use point estimates or probabilities of transitions between different system states. There's also another challenge related to complex relationships between uncertainty analysis. So this is related to the dependencies among different types of uncertainty that may be nonlinear. So selecting the right levels of precision for each analysis is going to be challenging. So for instance, a conservative analysis of each source of uncertainty can lead to a combined overall result that cannot guarantee compliance with, for instance, dependability, performance, and resource use of the system, because it is overly conservative. Also, analysis carried out more precisely can help avoid this limitation, but in general, they're going to require more data, they're going to entail larger models, and of course will involve higher computational overheads, and this is something that is not always affordable. There's also a challenge about multiple changes in uncertainty. So changes in uncertainty characteristics associated with a single source of uncertainty are already difficult to handle very often. So detecting changes that happen due to multiple sources of uncertainty and reapplying analysis that are required to assess combined impact is going to require compositional and incremental analysis techniques that are not currently available. So that is another challenge that we need to address. So beyond being able to model and analyze uncertainty interaction, an important challenge is being able to reason about ways to mitigate or reduce the impact of uncertainty interaction. So a key question to answer here is if the increase in expected system utility is justified by the cost of reducing the uncertainty. And this leads to a significant challenge, which is being able to predict the consequence of uncertainty reduction and to make trade-offs between the cost and benefits of doing it. So we have at least 3 different modes of or forms of interaction mitigation. So the first one we identified was dominance, where it may be the case that one form of uncertainty dominates or subsumes another one, and that by reducing the dominant uncertainty dimension, we're reducing the other. For example, uncertainty about the robot location, such as the one we have seen before, could be reduced by turning on a headlight, and this might completely dominate the uncertainty associated, for instance, about the robot's intrusiveness, if that's something that we care about. Another mode would be augmentation. So with augmentation, some uncertainties may be highly correlated with each other, but neither dominates the other. So uncertainty reduction of one type may positively affect the reduction of another. For example, uncertainty about the robot's location may be augmented by uncertainty about the safety of a robot, and reducing location uncertainty, we are going to be partially reducing the uncertainty in the other dimension, in safety. So the third mode would be conflict. So with conflict, reduction of uncertainty in one form may increase uncertainty in another form. So the example would be here trying to devote resources to increase the certainty about the robot's location, for instance. So this may remove resources for another aspect, such as the battery consumption. So for instance, if I add more sensors to improve the localization, I'm going to increase uncertainty about how much energy I have left in the battery. So ideally, techniques for uncertainty reduction should expose these trade-offs, like the one I just mentioned, and permit reasoning that strikes an appropriate balance between the different dimensions that we care about. So, but beyond these three categories, we also have challenges in exploration. So in exploration, one first challenge would be exploring multiple sources of uncertainty. So if in addition to overcoming these analysis challenges that we had before, exploration requires the ability to explore trade-offs between different configurations of uncertainty sources. So this challenge is more about open-ended exploration. So how can uncertainty models be integrated for exploration, for instance, in search-based frameworks, using different techniques such as game theory or probabilistic analysis? And in general, how do we use all these tools together to allow developers to explore what-if scenarios? We also have a second challenge about executable environments. And this is related to the fact that many of the sources of uncertainty require the dynamic behavioral analysis. So for uncertainty interaction exploration, executable environments are very valuable, because they provide the means to perform what-if scenario analysis, as I was mentioning before, and this requires a broad range of configuration capabilities to be able to combine different sources of uncertainty in a flexible manner. Digital twin frameworks, for instance, could be used. So far, they have been focused mostly on system functionality and performance, but in principle, they could be revised to explore uncertainty interaction, and this is something that still remains a challenge. So we also have another challenge regarding exploration, and it is related to uncertainty interaction visualization. So exploring uncertainty interaction is going to involve humans in the loop to configure uncertainty interaction model-based exploration, for instance, to identify uncertainty models or relevant data, or even appropriate analysis techniques. But they are also going to be involved when we need to interpret the results of the exploration. So because of this, we also need to have informative and interactive visualization techniques to support exploration tools. So far, I've been talking about the challenges in this different category, but this also leads us to think about, well, desirable traits that modeling notations would have if we want to start addressing all these challenges. So what kind of things would we require if we want to move forward with all this? So we compiled a list of desiderata, and we're going to go through that now. So starting with uncertainty patterns. So one way to address some of the challenges that we have in modeling, concretely, for instance, challenge M2 related to high-level modeling, is to develop a set of high-level patterns that account for different uncertainty sources. So these patterns should be able to express the uncertainty sources and the interactions that can have an influence on the properties of the system, and to combine them in an appropriate manner whenever required. So these patterns could also provide uncertainty mitigation actions in the form of model transformations or analysis for reducing uncertainty. And this would address all three mitigation challenges that we have mentioned before. Going forward with the list, we also have a hierarchy of domain-specific modeling languages. So a hierarchy of external DSMLs that contain references to system models allow specifying uncertainty interactions in a non-intrusive way, in contrast with other techniques that might involve the extension of the languages that are used to encode models in the knowledge base of the system, etc. So in fact, the uncertainty patterns that we have mentioned above in D1 could be specified with appropriate high-level DSMLs that would allow to indicate the occurrence of uncertainty sources and their interactions through the instantiation of patterns. And this would, again, contribute to addressing M2, the high-level modeling challenge. Then we would also use, in a complementary manner, lower-level DSMLs to specify how each uncertainty pattern is to be materialized in a specific system. And these lower-level DSMLs would be addressing challenge M3, which is the uncertainty interaction modeling. Also, the combination of high and low-level DSMLs would enable the specification of impact of uncertainty interactions and the ability to define uncertainty sources and interaction with different levels of details depending on the situation. So this would help to address challenges A1, which was the integration of uncertainty analysis, and also A2, which was the complex relationships among uncertainty analysis. So continuing with the list of desiderata, we also have one related to robustness. So the analysis of uncertainty models should yield results that are not affected in a significant manner by small changes, because these would result in mechanisms that would prevent very frequent reanalysis of the system, which is expensive in computational terms. So that sort of robustness is something that is also going to be desirable. We also have another desideratum related to reusability. So having a library of high-level patterns and non-intrusive DSMLs, of course, these should be reusable across different systems and models. And we also have compositionality in our list. This is another feature that the DSML should have. So in order to more effectively use a hierarchy of reusable DSMLs, this should be defined in a compositional fashion. So compositionality would enable us to address challenges such as M3, that was the one related to uncertainty interaction modeling. And this would be done by facilitating the description of interactions of uncertainty from multiple sources and also at different levels of abstraction. We would also be addressing partially A3, multiple changes of changes to uncertainty, by enabling the compositional and incremental analysis of potentially qualitatively different aspects of the system. And to finish our list of the desiderata, we have configurability. So configurability is related to the fact that models and their respective analysis techniques should be configurable both independently or also in combination. So this would provide better leverage for models and applicable analysis techniques so that we can perform uncertainty interaction detection and mitigation. And finally, we also have executability. So combined with configurability, uncertainty interaction exploration could be dynamically observed, having such executability in models. And this would lead to better informed decisions about mitigation ultimately, and hence addressing the different challenges that we have in execution and mitigation, in exploration and mitigation, sorry. And well, this leads us to conclusions. So in this talk, I have described the uncertainty interaction problem from a model-driven engineering perspective. And we have overviewed challenges in the representation, analysis, mitigation, and exploration of uncertainty interactions. We have also overviewed desiderata for future modeling notations. And well, we believe that this is an important area that deserves the attention of the community, and that these, following this path, will ultimately enable holistic approaches to build safer and more resilient adaptive software systems. Before finishing, I would also like to provide a couple of references if you're interested in further reading about this. The first one is a sourcing paper that is the uncertainty interaction problem in self-adaptive systems, where you can see further examples apart from the ones you have seen in this talk. And we have a more compact paper about addressing the uncertainty interaction problem in software-intensive systems that was published at Models last year, and this one is more focused on the ZNN example that you have seen in the talk, and it's more about the model-driven engineering perspective on which this talk has been focused as well. So with this, I finished the talk, and well, happy to take any questions you may have.
Thank you very much, Javier. Any questions?
Hi, can you hear me?
Yes, we can.
Well, thank you very much for the very interesting presentation. I was curious specifically on the safety aspect, how these uncertainty interactions would lead to safety implications and safety complications. Did you work in this particular direction? Probably the risk estimation, risk mitigation, and so on, specifically from the safety engineering perspective.
Mm-hmm. Yeah, I mean, so far we haven't explored any examples that are specifically about safety of systems, but for sure, we believe that this is a very important aspect to explore. Being able to yes. Sorry, I thought you were saying something. No, I was going to say that I think that all these addressing these challenges will contribute also to address all the challenges in the area of safety critical systems, of course, because there may be cases in which you have different uncertainty sources that perhaps are being considered individually, but still you may be missing some corner cases where a given level of uncertainty is interacting with another one, and this concerns some safety critical property. There are examples in areas such as autonomous driving, for instance, in which very subtle changes in the, for instance, the perception of the autonomous car, etc., can lead to situations that otherwise wouldn't be a problem if it wasn't because there's another uncertainty in the environment. And those interactions, I think that in general they're not easy to detect. So having some systematic techniques to model, analyze, and explore these uncertainty interactions in general could be very useful to address these kind of situations that are, of course, addressed for sure in some more ad hoc manner. So I'm sure that there are methods used in different areas of industry, for instance, in which these instances are addressed one by one on an ad hoc basis. But I think that having more systematic approaches to this is going to be useful, and of course can be an asset in the context of safety critical systems.
Okay. Thank you.
Mm-hmm.
All right. Any other questions? I have a question. So, Javier, you listed these numerous challenges, and they seem rather daunting when you look at all of them together. I'm wondering, can you see any ordering in which they might be easier to address based on dependencies or other factors? Or how do you see the community tackling them, because there are so many?
Yeah, I think that there's an order in some cases. I'm not sure if the order includes all the challenges, but I think that, for instance, and that's partly the reason why this talk is mostly about modeling, while the focus is on modeling, is because we first need to be able to represent the elements that we want to reason about. So if we don't have the means to represent different types of uncertainty in the first place, it is going to be difficult to build on analysis techniques or exploration techniques. So I think that at least modeling is a first reasonable step to start addressing all these challenges. Once we have the means to represent uncertainties and their interactions, I think we can start not only building, but perhaps also adapting existing analysis techniques to work on top of that. And analysis techniques will also be used to, for instance, build more ambitious approaches in terms of exploration, as I was mentioning, and mitigation. So I think that that would be, I definitely think that there's an order in which these challenges have to be addressed. At least it seems reasonable to do it that way.
Yeah, I agree. Suppose also because of the significant research effort that is needed to address them, it would be really useful if the community could assemble some sort of repository of use cases. Is there work in this direction that you are aware of?
Not so far. So that's indeed one of our intentions to start. Well, we have our modest efforts in start assembling a repository of cases where we can start exploring these ideas. But so far, I'm not aware of any other efforts in this direction.
Yeah, that's certainly something we would feel particularly useful to me, because before you embark on a significant research project, knowing about all of this would allow you to check your ideas and hypotheses early on in the project.
Right. Yeah, I agree.
All right. Any other questions for Javier?
I have one question maybe regarding to the presentation. So you mentioned different sources of uncertainty, and this approach is kind of like model-driven approach of modeling these different sources of uncertainty and see how they interact. Do you have different levels of or any difference in the levels of these different sources in the modeling? So do you consider all these sources as a separate levels of the modeling, or do they have a kind of hierarchy in the modeling? So how do you map these examples you gave in the beginning to these modeling elements for the interaction?
Yeah, there are different dimensions in there. So one of them is the different categories for uncertainty. So here I'm not talking about abstraction levels. I'm talking about different categories or groups of sources of uncertainty. And for this, to drive this preliminary work, we have used categorizations such as the one that was published by Danny Wines and other collaborators, where we have categories that concern the environment, model, adaptation functions, etc. So that would be one way to look at it. That's one of the dimensions. The other one is the fact that within a specific system, we might have different levels of abstraction. And of course, interactions may happen at such different levels, right? And interactions not only affect, there are direct interactions between uncertainty sources, but actually uncertainty is going to propagate through different levels of abstraction. So in this sense, there's also some preliminary work with some other colleagues that explores uncertainty interaction and propagation. And there we're explicitly considering ways to capture how uncertainty sources associated with flows of information go through different levels of abstraction in the system. For instance, interactions that may happen at the managed subsystem level and that propagate up the abstraction ladder to the self-adaptive layer. So I think that's also important to consider. And indeed, that's something that we're starting to explore as well.
Okay, that's very interesting. Thank you very much.
Simons?
Thanks, Javier. So have you, based on your experience, have you seen any common approaches, any groupings of approaches for analyzing the different challenges, like common solutions, or that could be leveraged or built on, or cross-cutting solutions that they could be used to address several challenges?
Yeah, so far we've come across several approaches that partially cover some of the things that we want to address, some of the challenges. but they do it in isolation. So in general, I mean, these approaches on their own do not have, let's say, enough critical mass in terms of covering, let's say, a broad range of the challenges that we have compiled. So I think that these approaches are indeed interesting to build upon. So to build things that will, of course, reuse some of the results that exist out there. But I think it's difficult to find approaches that cover explicitly uncertainty interactions. If we talk about individual cases and things like that, I think that that's also part of our work, like trying to compile information about experience from people in industry and in academia to inform also our research, which is something that that would be very useful. But for the time being, we have a limited number of examples and cases to work with.
I think that you answered that pretty straight. So, but I think, you know, going back to what Radu said, it's if you assemble a set of use cases that people could also use, it would be like assembling also, which would be more difficult, like a body of knowledge of techniques that they have been used or applied, and populating a multidimensional body of knowledge, both for problems and solutions for this particular topic. Okay.
Yeah, definitely.
Right. Any other questions? All right. If there are no more questions, then I would like to thank you again, Javier, for a very interesting talk and thought-provoking. We now have plenty of work to do for, I think, many years to come to define better this problem and tackle it. And thank you, everyone, for asking questions and participating in the seminar. I shall see you again in 2 weeks' time. Bye now.
Thank you. Thank you.